this chapter, we will be introducing and studying derivatives. In this lesson, we will be studying the tangent problem.
Okay, everybody. So now we're going to talk about the tangent problem. Now we are really getting close to what calculus is, or where at least calculus begins, okay? Now, before we talk about the tangent problem in particular, and actually what I've got written here isn't actually going to address the problem. I will talk about it in a second. Is the first thing we got to do here is define what a tangent line is, okay? And at first that might seem like a pretty obvious thing. You've probably talked about it a lot in the past. You've probably done it with little bits of geometry that you've talked about. You've probably even seen it in a physics class. But we want to talk about a little bit more specifically about what a tangent line is, okay? It's a line that touches a curve only once within the neighborhood of the point of tangency. Now, this whole idea of touching, that's kind of a nebulous concept. What does that mean to touch, right? So here, for example, we know that this is a tangent, but over here, if we take a quick look over here, this right here isn't a tangent. Now, it looks like they're both touching, but in this case, I'm going right through the curve. So what we're looking for here is we're looking for a line that touches the curve without going through the curve. Now, the thing is, even that is not actually a great definition of tangent. And you're going to see some examples later on in this course where turns out the tangent line does, in fact, go through the curve. And you'll see some exceptions here. So what we're looking at right now is not the best definition, but it certainly gets us quite a ways further ahead than this idea of just touching. Now, when we talk about a neighborhood, that's not just me using a kind of math, quote unquote, slang, if you will. Actually, the word neighborhood in math has a very specific meaning. And what a neighborhood is it's a circle with a variable radius centered on a certain point. So right now, over here, let's take a look at this diagram. Okay, here's my point of tangency. This is where my tangent line, PT, touches that circle. Now, this right here, what I'm drawing, that's my neighborhood. Okay, and now I can make that as big as I want. I can make this I can make it even larger, right? This huge neighborhood here. But the point is, what a neighborhood is, it's a circle that you draw centered on a specific point. Okay, so when we do that, what we're going to do here is we're going to create another function here. So we're going to let f be the curve. So here's my circle. I'm going to let that be f. Then I'm going to let g be the tangent line. So here's my g, okay? G is my tangent line. I'm going to create a new function here, call it h, okay? And what's going to happen here is I'm going to take f and I'm going to subtract g for every x value inside this neighborhood. Now, take a look. When I do that, remember, f is the circle, g is the function. F is the circle, g is the function. So if this is my x-axis right here, so here's my y-axis, here's my x-axis, every value of x in this neighborhood, every value of x they plug in here, when I evaluate that, f minus g, circle minus the line, the result's going to be negative. Except for possibly at that point of tangency where it would be 0. But for every point inside that neighborhood here, it's always going to be either positive or negative. Okay? Now, over here, you see the same sort of thing happening, right? We're on both sides, okay, on both sides of that point of tangency, okay? The tangent line is, let's say, above the curve. Or we could draw it below the curve, okay? Now, over here, that's not true. On the left-hand side of that point of tangency, the difference between those two, if I let f be this function and g be the tangent line, okay, it's going to be negative here, but it's going to be positive on this side. So it's switching signs here. That's usually a very good sign that this is not a tangent line. Now, it turns out that's not always the case, and we will see some exceptions to this rule as we go along here. But anyway, so now we've got a little bit more of a little bit more precise definition of what a tangent is. Now let's talk about specifically what the problem is for the tangent line. Okay, and actually the problem, I'm just going to switch here. The problem comes more out of your experience in like a physics class than it would be in necessarily a math class. So in physics, okay, or in science, any kind of science you've probably dealt with here, you have probably, for example, done a graph where you had, let's say this was time and this was distance, and you had some sort of function here, whatever, something like this. We've probably all had the experience that what you were supposed to do, what your teacher told you to do with your distance time graph is you were going to draw a tangent line right there. Now, mine's not beautiful, but you get the idea. So I drew the tangent line right here. Here's my value A. And you were told that the slope, if we call this line 1, the slope of line 1 was going to equal the velocity, okay, at point A, or at time A. Okay, so the slope of line 1 right there is going to be the velocity of whatever object it is that we're modeling here at point A here, or at where x is equal to A, or the t is equal to A, I should say. Now, here's the thing. That was probably fairly easy to do. You took out your clear ruler, you kind of lined it up here, and you drew it here. Now, the truth is, if you've got a lot of people doing this, you will probably have a little bit of variation, right? Like you might have somebody else draws the line and it's a little bit steeper. Okay, somebody else draws the line, it's maybe not quite so steep, sort of thing. But there's usually not much variation. Usually we're all going to be within the same ballpark here. Okay, so there's something about this process. We can look at it and kind of instinctively get a sense of what the slope of the tangent line would be there. But here's the thing. Slope, okay, slope, the formula for slope is y2 minus y1 over x2 minus x1. You might have used a different notation for that in the past, but the thing is you need 2 points. 2 points to evaluate a slope, okay? 2 points to evaluate a slope. What we're looking at right here is we took this point along this curve and we basically drew, if you will, a line to give us the slope, but we're looking for it at that specific point there. So we're really only looking at 1 point, okay? There's 1 point here, and we're able to draw a very specific slope, okay, a line with a very specific slope at that point here, but just at 1 point. So the question is, how are we doing that? And if we can do it in this context with like a clear ruler, shouldn't we be able to do it for any kind of a curve? Shouldn't we be able to do it algebraically? Okay, and the answer is actually yes, we can. Okay, even though our slope formula requires 2 points, okay, we can kind of engineer this situation here so that we can in fact find this slope, okay, the slope of this tangent line at this 1 point along a curve. Now, the reason why this works here, the reason why we're able to do this here in this physics context is because what we're doing is we are actually looking at the neighborhood of that point. We are using the points, okay, on both sides of the curve, and we are both sides of that point of tangency, and we're drawing the line. We're kind of eyeballing it right now. We're drawing that line so that it really does just glance off the curve at that particular point. But we are using the neighborhood, okay? So it's not like if I drew a dot right here, okay, right there, I can't just draw a tangent line to that. I mean, what the heck? What does that mean? I have no idea. Okay, you can't do it with just 1 point. What we're going to do here is we're going to use 1 point and its neighborhood. Okay, neighborhood to do this. And now this is what I'm going to show you. So we're going to take a quick look at an example here with a parabola, and I'm going to walk you through how we're going to use this neighborhood to figure out what the slope of that tangent line should be. Okay, everybody, so now we're going to answer the question here. We're going to find the equation of the tangent line to the graph y equals x squared plus 2 at the point 2, 6. Okay, so let's take a quick look at what this is going to look like first of all. So here's our coordinate plane, and then here's our parabola. I'm not very good at drawing this, but you get the sense of it. And here's its vertex there, the point 0, 2. Now the point 2, 6, now forgive the scale. Let's say that the point 2, 6 is somewhere out here. what we're interested in is the equation of the tangent line looking something like that. Okay, we want to find the equation of that line right there. To come up with the equation of that line, okay, I need to have either 2 points or a point and the slope. Well, I've got a point. I've got the point 2, 6. I know that that is on my graph right there, okay? 2, 6. Now, again, forgive the scale here. It's way out of whack, but it'll give you a better sense of what's going on here. Now, in order to do this, what I need to do here is we're not going to be able to just jump in and get the slope. What I'm going to have to do here actually is come up with another line here. In order to come up with a slope, I need 2 points, okay? So this is really what I've got to do here. I'm going to draw a point on the graph right there. Now, I realize that that point is not actually on my tangent line. But if I connect this point that I just came up with the one that we have originally, we get this line right here. Okay, that's a terrible drawing there. But I think you get the idea here. If you take a look at it, that line that I just drew is relatively close to this tangent line. It's not exactly the same. It's off by a little bit, but it's close. And that's actually what we're going to do here is we're going to come up with a line that sort of approximates the line that we're looking for, that tangent there. Now, we are going to call this line here the secant. It's called a secant because it actually intersects the curve that I'm working with here twice. It intersects it here and it intersects it here. I know the coordinates of this point right here are the coordinates 2, 6. Up here, I don't know what the coordinates of this new point actually are. I have no idea. I might just call it x comma y. Now, like I tell my students, I can actually do a little bit better than this. Okay, I can do better than y because I know what y is equivalent to. I know that if I pick any point on that curve, the coordinates will be x comma y, yes, but x comma y could be any point on the plane. If I want to make sure that they're specific to being on this parabola, then the y coordinate has to be related to the x coordinate. And in this case, this is how they're related, x squared plus 2. Okay? So now that I've got 2 points here, now granted, I don't have this point specifically. Okay, it's kind of a general point. Okay, I don't know what x is at this point here, but you're going to see that that's actually works to my favor. I can actually come up with the slope of this line segment. Remember, slope is y2 minus y1 over x2 minus x1. And so y2, x squared plus 2 minus y1, 6, okay, over x2 minus 2, x1. So my slope, the slope of the secant line, okay, the slope of that red line there, is going to end up being x squared minus 4 over x minus 2. Now, I'm going to change color here. I'm going to turn this into a green here. If I move that point closer, okay, and closer to that point of tangency 2, 6, then what happens here is the line pivots. That tangent line pivots, and it gets closer and closer and closer to that actual tangent line. Now, I've got a bit of a mess going there. Okay, but let's take a look here. Let's just erase this little bit right here. Let's kind of start that again. Okay, so let's go back here just to illustrate what's going on here. Okay, so here's my parabola, and I'm gonna expand this out a little bit more here, something like this. So let's clean this up. Let's get rid of this. So I want to find the point of tangency. Let's say I want to find the equation of this tangent line right there. So it's going to look something based on my curve, something like this. So what I do is I pick this point way up here to start off with, and when I connect them, there's my secant line. That's not a very good approximation to that black line, the tangent. So I move that point closer. Draw a new line. That's a little bit better. then what I do is I'm going to just move that. I'm going to move that closer. Let's use the blue here. I'm going to move that even closer. And so what's happening here is as I move that point, that second point, that x comma x squared plus 2, as I move that closer and closer and closer to that point that I was given at the beginning, 2 comma 6, the slope, this slope right here, starts to approximate the slope of the tangent line. Now, hopefully, after describing it like that, you get a sense of what I'm actually doing here. Okay, so right now I've got the slope of my secant line, okay, and I know that that's going to be x squared minus 4 over x minus 2. But I can change the slope of that secant into the slope of my tangent line by taking the limit as x approaches 2. As the x coordinate right here gets closer and closer to 2, this whole point gets closer and closer to the point 2 comma 6. So if I take the limit as x approaches 2 of my secant slope, that's going to give me the slope of the tangent. That's the beautiful thing about limits. Okay? Now, bear in mind, I never actually get there. Okay? I never actually get to 2. All we're doing is we're pointing at where this is, what this is approaching. And now we've already seen, if I plug 2 into this right now, I will get 4 minus 4 over 2 minus 2. So I'll get 0 over 0. So what I need to do here is I need to factor the numerator, x minus 2, x plus 2 over x minus 2. And then I can see here that x minus 2 divided by x minus 2 will end up being 1. So that will cancel per se there. Now, canceling because it becomes 1. Now, remember, that's undefined at 2, but my limit actually never gets there. I never actually get to 2. I only approach 2. But as I approach 2, this expression, now I would plug that in, okay, into what's left over here. So this is going to be the limit as x approaches 2 of x plus 2. And my answer is going to be 4. So the slope of my secant line, as I move that secondary point closer and closer and closer to the point of tangency, the slope of that secant line gets closer and closer and closer to the slope of the tangent. What's the limiting value right now? The limiting value is 4. That, therefore, is the slope of the tangent. And now I can write my equation in point slope form. I can say, therefore, my equation will be y minus 6 is equal to the slope of the tangent 4 multiplied by x minus 2. That's the equation of the tangent line. Okay, so this is how we figure out, this is how we get around the tangent problem. The tangent problem is, how do you determine, you can draw the tangent line against a curve, but how do you figure out the equation of that tangent line, or more specifically, the slope of that tangent line if all you've got is one point? And the answer is, what we do here is you use the neighborhood of that point. Now, if you're looking at this thinking, well, wait a minute, we didn't actually talk about the neighborhood. Yes, we did, because as soon as you start using a limit, remember that a limit only exists if you can approach from both sides here. And that is exactly what happens here. My general point here, x comma x squared plus 2, that could have been on either side of that value that I'm looking for. Anyway, now let's generalize this idea.
Now we're going to take a look at the slope of the tangent in a more general form.
So now we're going to do the same thing that we just did, but we're going to do this in a more general case. Okay, so we're going to start off with the, we're going to find the slope of the tangent line to the curve f of x at this point, and we're just going to let x be a. So then our general point here is going to be the point a comma f of a. So we will come up with some extra point on here. Let's say, and I'm going to do this on the other side of the point, on the left side of the point this time. Here's my x comma f of x. So we are going to find the slope of this secant line. Then what we're going to do is we're going to take this point right here and we're going to slide it along the curve, okay, until we find, or until we approximate incredibly closely, super closely, so closely that we're actually looking at the slope of the tangent line. And the way we do that here is we're going to take the slope of that secant line, that's the slope of the line connecting those two, And then we're going to take the limit as delta x as the difference in x between these two here. Okay, the difference between my x and my a here. We're going to let that go to 0. Now, remember, delta y over delta x, that is the formula for the slope of a secant line. And so now what we're going to do very specifically here, and this is actually the equation that we're looking for, the expression that we're looking for, the slope of my tangent line is going to be the limit as x approaches a, okay, as the x coordinate approaches a, because as I let the x value approach the a value, what that's going to do is that's going to push this point along the curve, right? Because remember, the y coordinate also depends on x. So as I move that x value forward here, it's going to force the point to slide along that curve until it gets closer and closer and closer to this guy right here. And the slope of that secant line is going to be f of x minus f of a all over x minus a, change in y over change in x, and then this limit as x approaches a is what's going to force this to become the slope of the tangent line. Okay, so that's one way of looking at it. Or another way to do this is instead of talking about the delta x, we're going to let h represent the delta x. And I'll show you how this works here. What we're going to do now is we're going to take our point here, f of x. Now this is going to be our original point. So this is where we're going to find our point of tangency. So this time we're going to change our focus a little bit. Then what we do is we introduce a slightly different point here, and we're going to let h be this horizontal translation. Now we are doing something really the difference is minor. It's so minor. But the way we apply the two expressions that we're about to come up with are quite different. Okay? So we've got x comma f of x right here. That's the point of tangency that we're trying to find the tangent line to that point. We introduce a very, very small plus h to x. Now that means that the y coordinate becomes f of x plus h. Now, applying the same expression for slope here. So the slope of the tangent is still delta y over delta x. That's the slope of the secant, and we're going to let that delta x go to 0. We're just going to bring this point closer and closer and closer. Now, what that looks like for us right now is that's going to be y2 minus y1 over x2 minus x1. So y2 minus x1 over x2 minus x1. Not much of a change here, except remember h was the horizontal translation. So what we're going to do here is we're going to let that h go to 0. Okay, that's going to be the delta x here. And actually in the denominator, when you simplify that expression, you get x plus h minus x. That's just going to be h. And this right here is our other expression for the slope of the tangent line. Okay, now if you get rid of the limit as h approaches 0 here, this expression right here, once again, is the slope of the secant line, but we actually give it a name here. That's actually called Newton's quotient. Newton's quotient, it is the slope of the secant line. As soon as you throw in the limit as h approaches 0, that then becomes the slope of the tangent, okay, to the curve at the point x comma f of x. Now, notice what I just said here and how this differs from what we've done previously here. I just said that once you take the limit here, this is going to give you the slope of the tangent at the point x comma f of x. I'm not using a specific value for x. I'm still using the variables. Up here, this found us the slope at the point a comma f of a. Remember that a, in this case, is going to represent a constant, a given value. You would know the numeric value of a in this context. Here, you might not be given a value for x. And so what we're doing here is we're getting this thing in general. So there is the work that we do is very slightly different between this expression here and this one down, and this one down here, but the result is significantly different. We call this expression right here first principles. Okay? And again, just to state it here, without the limit, that's Newton's quotient, or some people call it the difference quotient. But with the limit, and here it is, everybody, with the limit, we call it a derivative. Okay, so this right here, you kind of ignore this part right here. The slope of the tangent line, going to equal to f of x plus h minus f of x over h. We call that the derivative of a function. It is the slope of the tangent line at a point. So now we're going to find the equation of the tangent line to the curve y equals the square root of x minus 4 plus 1 at the point 5, 2. And we're going to do this using two different methods here. So the first method we're going to use here is we're going to find the limit. We're going to find the slope of the tangent by taking the limit as x approaches a of f of x minus f of a all over x minus a. In this particular case, that's going to look like this. That's going to be the limit as x approaches 5. That is the x coordinate of the point that we're interested in. Now, f of x is going to be the function. So x, the square root of x minus 4 plus 1 minus, now f of a, okay, the y coordinate of the point we're interested in is 2. Okay, all over x minus 5. This is the value of a in this particular expression. Now, let's just simplify this as much as we can here. So that's going to be the limit as x approaches a. This will be the square root of x minus 4 minus 1 all over x minus 5. Now, if we plug 5 into this, we're going to get the square root of 5 minus 4, which is the square root of 1. Minus 1 is going to be 0 over 5 minus 5 is 0. Okay, so this is an indeterminate form. Now, think back to how we did this with limits. What I'm going to end up doing, sorry, not with limits, that's not what I meant to say. Remember how we did limits when we had radicals in them? What we're going to do here is we're going to rationalize the numerator. So we're going to multiply the numerator here by the square root of x minus 4. Whoops. I don't know why I did that. The square root of x minus 4 plus 1. Okay, square root of x minus 4 plus 1. We're going to rationalize that numerator there. And so now we're going to get the limit as x approaches 5. That's going to end up being x minus 4 minus 1, okay, all over x minus 5 times the square root of x minus 4 plus 1 in the denominator. Now, x minus 4 minus 1 is going to be x minus 5. And so we know that this and this are going to cancel each other out. They're going to become 1. And so now if I plug 5 in, now bear in mind my numerator is now 1, okay? The denominator is going to end up being the square root of 5 minus 4, which is 1, plus 1 is 2. So when I plug 5 in there, I'm going to get 1/2, which means, therefore, that the equation of our tangent line is going to be in point slope form. That's my favorite form. Y minus 2 is equal to 1/2 multiplied by x minus 5. That's the equation of our tangent. Now, that is one way of doing this. Okay, that is one way of doing this. The second way of doing this is to use first principles. Okay, and to let this m equal the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, this is going to be a good opportunity for you to really catch the difference between these two expressions for the slope of the tangent line. They are, like I said before, they are very, very similar, but they play out substantially differently as we go through this. Okay. Additionally, when you're using first principles here, it will become very, very clear very quickly whether or not you really understand function notation. Okay. It's a very, very common thing for people to misunderstand what this means to have a binomial within the within function notation the way it shows up right here. So be very careful with this. So the slope of our tangent here is going to be the limit as h approaches 0. And in this case here, our function is going to be the square root of x plus h minus 4, okay, plus 1 minus, I'm going to put this in brackets because I got to remember to do this correctly here, x minus 4 plus 1 all over h. Okay, next step. This is going to be the limit as h approaches 0 of, I'm going to let that negative go through. This will be the square root of x plus h minus 4. But when I put that negative through, I'm going to get this plus 1 here. Then I'm going to get this minus the square root of x minus 4 minus 1 all over h. All right. Now, notice that the ones are going to disappear there. And what I'm left with here is the square root of x plus h minus 4 minus the square root of x minus 4. So I've again got a limit with radicals in them. So what I'm going to do is I'm going to multiply numerator and denominator by that binomial conjugate. So the square root of x plus h minus 4 plus the square root of x minus 4. Oops. Okay, and we multiply that numerator and denominator here. So x plus the square root of x plus h minus 4 plus the square root of x minus 4. Okay, so now this will end up being the limit as h approaches 0. Now, we've created this difference of squares in the numerator, so we are going to get x plus h minus 4 minus, now, minus, the reason why this is subtraction right here, the last thing I wrote was subtraction, change my color here, is because this was a negative, this is multiplied by a positive. So when I multiply the negative root of x minus 4 by the positive root of x minus 4, I'm going to get a negative as a result, okay? Still, the radicals will cancel, I'll be left with x minus 4 over the square root of x plus h minus 4 plus the square root of x minus 4. Now, in the numerator, so I'm still taking the limit as h approaches 0. In the numerator, watch what happens when you distribute that negative through to the x and then to the negative 4. So this is going to become up here. This will become negative x. Whoops. No. Negative x. And then that's going to become positive 4. And when you simplify that numerator, I'm going to get x minus x goes away. Negative 4 plus 4 goes away. All you're going to be left with here is the h. Oops. Sorry, and I miswrote this in the denominator. I forgot about that h right there. Sorry, that right there, that h should also have been down there. So it is down there. H over h multiplied by the square root of x plus h minus 4 plus the square root of x minus 4. Now, h divided by h is going to get you a 1. And now we've got this amazing little thing that happens here. Now, if I evaluate the limit, if I let h go to 0, all that's going to happen is that this h right here, the one that I'm underlining here, is going to go to 0. And notice that in the denominator, you're going to be left with the square root of x minus 4 plus, well, that looks terrible, but plus the square root of x minus 4, which means I'm going to have 1 over 2 times the square root of x minus 4. Sorry, that looks so terrible. The computer here is writing a second or two after I've finished writing here. But anyway, so now we're left with this expression, 1 over 2 multiplied by the square root of x minus 4. Now, this is not the answer that I'm specifically looking for. I am looking for the slope of the tangent line. But what I found here is really neat. What this is this is an expression for finding the slope of the tangent at any given value of x. In fact, this right here is all slopes of the tangent. Okay? So now that means I can evaluate, if I evaluate this right here at 5, when x is equal to 5, if you plug 5 into that, you will get 1 over the square root of 2 times 1, 1 over 2 multiplied by the square root of 1, which is just 1/2. And so, and it's already giving me a time down here. So y minus 2 equals 1/2 x minus 5. Okay, now we're going to do a similar question. We're going to find the equation of the tangent line to the parabola y equals 2x minus x squared at the point 2, 0. Whoops. Okay, And we're at the point 2, 0. That was weird what just happened there. Let's fix that. Okay, now again, we're going to apply the two different methods of doing this. So our first method here works because we know very specifically what the point of tangency is. So we're going to take the limit as x approaches a. This will be of f of x minus f of a all over x minus a. In this particular case here, that is going to be the limit as x approaches 2. That's the x-coordinate of the point of tangency. F of x is the general parabola, so it's going to be 2x minus x squared minus the y-coordinate of the point of tangency is 0 all over x minus a, the x-coordinate of the point of tangency is going to be 2. And so now we're left with the limit as x approaches 2 of 2x minus x squared all over x minus 2. Okay, now we're looking at a limit here. We've got this rational expression. I'm thinking I'm going to have to factor here, okay? Just like in the previous question, we had radicals in there, and so we had to rationalize. Here, with a rational, I'm thinking we have to factor. So if I take out a common x out of the numerator, I'm going to get x over 2 minus x all over x minus 2. Oh, those two factors look very, very similar, the 2 minus x, the x minus 2, but they're not exactly the same. So what I'm going to do here is I'm going to make this one up here. I'm going to make it pretty. And what I mean by that is, notice that I've got 2 minus x. I don't really like it when the x is last. I like it when x is first and the constant is last. So I'm actually going to switch the order of those two. I'm going to make that negative x plus 2. And changing the order, as long as that negative follows that term around, changing the order doesn't matter. Now what I'm going to do is I'm going to factor the negative out of that expression to get negative x. There was an x out front, and that'll leave me with x minus 2 over x minus 2. Now, x minus 2 divided by x minus 2, or those are going to go away. And now if I plug in my limit, okay, I've got this negative x there. If I now let x equal 2, my limit's going to end up being negative 2. And so now my equation, now that I've got the slope of the tangent line, my equation is going to be, if I use point slope form, y minus 0 is equal to negative 2 times x minus 2. And that y minus 0 looks ridiculous, so I'm not going to write that. Instead, I'm going to distribute the negative 2 through, so negative 2x plus 4. That's the equation of my tangent line. Now, that's the first way of doing it. The second way of doing this is to utilize first principles, okay, where the slope is going to be the limit as h approaches 0 of f of x plus h, minus f of x. Sorry, I'll clean that up. Okay. Minus f of x all over h. Now, in this case, that is going to be the limit as h approaches 0 of 2x plus h minus x plus h squared minus bracket 2x minus x squared, okay, all over h. Now, these first two terms here, remember, those are coming from this f of x plus h. I've just gone back to the function. I've replaced x with x plus h in both cases here. Now, my next step here is going to be to expand that all out. Now, first principles frequently does this. It's going to get a little bit messy up at the front here. So this is going to end up being 2x plus, 2x plus 2h when I distribute the 2 through, minus now x plus h squared is going to be x squared. There's going to be a 2xh in the middle there, but that negative in front distributes. So minus 2xh plus h squared, but there's a negative in front, so it's going to be plus h. Sorry, I just said there was going to be a negative. There's a negative in front, so that negative is going to distribute. So negative h squared. And then in the second this last term here, I should say, the negative will distribute through to get negative 2x plus x squared. And this is all over h. Now, one of the really fascinating things about first principles is when I simplify this, this is all over h here, notice that when I simplify this, the 2x term here cancels with the 2x term here. The negative x squared cancels with the positive x squared. And what I'm left with here are three different terms, but notice that each one of them has an h in it. And it's so interesting that with first principles, that always happens. And so now I can factor out the h out of those expressions, and I'm left with 2 minus 2x minus h. Okay, well, h over h is 1 for every value of h other than 0. And granted, I never get to 0. I'm approaching 0, but I never get there. Whoops. Sorry, I don't need to do this now. I can actually skip to the end here, because now I'm going to take the limit as h approaches 0. I'm going to substitute in 0 in for that h right there, and I will be left with 2 minus 2x. And again, what's really neat about this is that this represents the slope of every tangent line to the curve. All I got to do is substitute in the specific x value of the point that I'm looking at, and it will give me the slope of the tangent line at that x value. Now, the reason why this works, by the way, is because we're working with functions, not relations right now. There is only one point on this curve for any given x value. I mean, that's one of the really important properties of a function here. So we can do this quite simply here. Now, it's not to say that you can't do it when you got a relation, when there's x's and y's in there. It's just a little bit more complicated, and we'll take a look at that later on. But now, if you want to figure out what the slope is, our notation here, you might do this. You might say m with this line here, which means evaluated at, and down here you write x is equal to 2. Okay, so this is our slope evaluated at x equal to 2. And if you plug 2 into that, 2 minus 2 times 2 is going to give us negative 2, just like we got with the previous example here. So we can see right there that the slope is negative 2. And just like we did previously, we would work this out really quickly to get that our tangent line would be the line y equals negative 2x plus 4, just like we did in the previous method that we used. Okay. Now, granted, first principles is more work. Okay, it's a little bit more work. Things get a little bit ugly. That step gets quite long. It simplifies down, and even when you get it down to a simplified expression, you still might not have the slope you're looking for. You're going to have to plug in an x value to get it. But we're going to see in just a little bit here why this particular method here, this first principles, is so important and so very useful to us. I hope this helped.